if we're using this formula to create a general term and then calculate the indicated term, then in this case, my term 1 is equal to 5. My common ratio is equal to term 2 divided by term 1, or 3. And I can jump right to stating that my general term, in this case, would equal 5 times 3 to the power of n minus 1. I could use that to solve for any term. If it wants us to calculate term 9, then I'm going to say that term 9 is equal to 5 times 3 to the power of 9 minus 1, which is going to give me 32,805. In the second case, I can see that term 1 is equal to 1 over 3. My r value is equal to 1 over 3 divided by negative 1 over 6, which is going to give me an r value of, oh, sorry, I did those backwards. Term 2 divided by term 1. Negative 1 over 6 divided by 1 over 3, which gives you an r value of negative 1/2. If I know that my r value is negative 1/2, then I can say that the general term, solving any term I need to in this sequence, is going to be 1/3 times negative 1/2 to the power of n minus 1. If it wants us to calculate the seventh term in this sequence, then term 7 is going to equal 1/3 times negative 1/2 to the power of 7 minus 1, or to the power of 6, which is going to give me 1 over 192. Now, if I need to determine the number of terms in a geometric sequence, then I can say that I can use the general formula to write and simplify an equation which could be used to solve the general terms. If I know that my first term is 32, my common ratio is 64 over 32, or just 2. And my final term value is 16,384. Then I can say that if the value of any term is the first term times r to the power of n minus 1, then 16,384 would equal 32 times 2 to the power of n minus 1. Or, when I divide both sides by 32, 512 is equal to 2 to the power of n minus 1. Now I need to be able to solve an exponent. Well, Janice is using the guess and check to write each side of the equation with a common base. So, Janice said that if I have 2 to the power of n minus 1, then she tried because we know that the n has to be a natural number, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, going on and on until she found 2 to the power of something that gave her 512. And she said that was 2 to the power of 9 was what gave her 512. If that's true, then that means that, looking up at the top here, the n minus 1 has to equal 9. So the n value, when I add 1 to both sides, would be 10, and there's 10 terms. Gary used a graphing calculator to solve this, where he said that the left side and the right side of this equation have to be equivalent, which means that he can create two functions and then solve for where the functions intersect. If he said that y1 was equal to the left side, 512, y2 was equal to the right side, 2 to the power of, in this case, x minus 1, then he just graphed it out, used the second trace 5 to solve the intersect, and they intersect when x was equal to 10. And he knows that there is 10 terms.